Hello, this is part 1 of battery thermal modeling and ROM generation video. First, let's see why battery thermal modeling is important. As you know, batteries generate heat during operation. Battery lifetime and performance depend on operating temperature. With a higher temperature, we can increase the capacity of the battery but decrease its lifetime. Therefore, thermal management of a battery is crucial to its performance and lifetime. Now that we know why battery thermal modeling is important, we want to see how a reduced order model can help in battery modeling. Reduced order models, or ROMs, are simplifications of high-fidelity complex models. They capture the behavior of these models so that we can quickly study systems' dominant effects using minimal computational resources. To explain the importance of ROMs in batteries, imagine you drive your EV from home to office in the morning. The load on the battery changes in different operating modes. You start your car, you push on gas, then you stop at the light, then you're stuck in the traffic, and you do all these actions several times just for a simple commute between your home and your office. This load can be different on a different day. The outside temperature can also be different depending on the time of the day or the condition of the weather. Performing a high-fidelity simulation for all these scenarios can be computationally very expensive. Now imagine that you can create a ROM that captures the thermal behavior of the battery and you can run it in a much shorter time with a much less computational resources and still have accurate results. This is how a ROM can help, and in this video I'm going to show you how to generate it using Ansys tools. Okay, now let's look at the battery that we want to model. This battery has 2 cells and is seated on a water cooling plate. Water enters the pipes at 20 degrees Celsius. In this demo, we will generate a linear time invariant type of ROM. Before generating an LTI ROM, we must decide the inputs and the outputs to the ROM. In this demo, I have 3 inputs: average volumetric heat generated in cell 1, average volumetric heat generated in cell 2, and tap electric current. The outputs of the ROM are average volumetric temperature in cell 1 and average volumetric temperature in cell 2. LTI ROM generation and validation for a battery consists of 4 steps. In the first step, we solve a conjugate heat transfer model in Ansys Fluent with all the ROM inputs set to 0. The goal of this step is to generate an initial condition for step 2. In the second step, we generate training data in Ansys Fluent. In the third step, we generate an LTI ROM from the training data that we obtained in step 2 using Ansys Twinbulider. And finally, in the fourth step, we validate the ROM results by comparing them with the high-fidelity CFD results obtained from Ansys Fluent. In the first step, I will show you how to set up a conjugate heat transfer simulation for a battery in Ansys Fluent. The goal of this step is to set up a steady-state simulation and obtain the flow field of the water in the cooling plate. I have already loaded the mesh file. For this simulation, I use pressure-based solver, and I'm going to run the calculation in a steady state. I have also turned on the energy equation. Since the Reynolds number of the water flow in the cooling plate is small, I set the viscose model to be laminar. As for material, I have added water liquid from Fluent material database. I also generated a material called active material, which has a density and a specific heat as you see on the screen, and an orthotropic thermal conductivity with the value that are set and you see here on the screen. I will use this active material for the battery cells. I have also added aluminum and copper from Fluent material database. As you can see, I have 2 fluid zones. I've set the material of water liquid for each of these fluid zones. For the battery cells, I select the active material that I created earlier. I have selected mass flow boundary condition for both inlets with a mass flow rate that you see on the screen and a temperature of 20 degrees Celsius. For all the external boundaries of this battery module, I set a convection heat transfer coefficient of 5 watt per meter square Kelvin and a free stream temperature of 25 degrees Celsius. So here I'm done with the setup of the simulation. I'm gonna go ahead and initialize the calculation using hybrid initialization. Next, I will run this calculation until the convergence is reached. The calculation of the steady-state conjugate heat transfer simulation is finished. Here we see the streamline of water flow in the pipes of the cooling plate. Now I move on to step 2. In the second step, I turn on the battery model. In the battery model panel, I select CHD coupling solution method and I enable the Joule heat in passive zones. Under the conductive zones tab, I select cell 1 and cell 2 as active components and I can display them, and the bus bar and the tabs as passive components, and I can display these components as well. Under the electric contacts tab, I select the faces for the external connectors. Also, I make sure that under model parameters, the energy source per battery and the total electric current is set to 0. Under Advanced Options tab, I click on Battery ROM Toolkit. In the Battery ROM Toolkit, I select LTI ROM type. Under ROM input parameters, I click on Volume Heat. Here, I select cell 1 and cell 2 on the left-hand side. I also enter a value of 10 watt for the volume heat for these cells. The value that you use doesn't matter. It just must be large enough to result in some change of temperature in the battery cell. Then I click on Add Individually here. I also make sure that the input tap current for Joule heat option is checked. I put in a value of 100 ampere, but the exact value again doesn't matter. It just needs to be large enough to result in some change of temperature. Then under LTI ROM output parameters, I click on cell zone average. I then select cell 1 and cell 2 on the left-hand side and add each individually. In the transient setup, I set the maximum type to 6000 seconds with an initial time step size of 0.05 second and a maximum time step size of 10. I kept the default values for the rest. Now I'm ready to run the training simulations by clicking on Run Training. After the training simulations are finished, you will notice that in your working directory, a folder named LTI is generated. Also, notice that Fluent automatically writes a case and data file called lti-rom-initial_file. We will use these files later in step 4 for running a validation simulation. In this folder, you should see these files. In input_port names.txt file, you see the names of the inputs in the first row and the names of the outputs in the second row. In input_step_input_values.txt file, you see the value that you entered for each of the inputs. In my case, I have entered 10 watt for the volumetric heat inputs, which are the first two values here. I also use 100 ampere for electric current. As you see here, the third value is 10,000, which is 100 to the power of 2. The square of the value you chose for the electric current is in fact the input to the ROM, because as you know, power has a linear relationship with the square of current. You should also see 3 out files called joule_heat, vol heat underscore cell 1, and vol heat underscore cell 2. These files include the response of the battery, which is the raise of temperature of the cells to the 3 inputs that we have defined. At this point, I suggest you to copy the content of one of these files to an Excel sheet and create a plot of temperature versus time to ensure that the solution has reached steady state. With this, I wrap up the first part of this video series. I hope you enjoyed it. Thank you and have a good day.